Welcome back to another vBrownBag build day video here for the HP SimpliVity 380 build day, and I'm joined by one of my longest term friends in the industry, Mr. Brian Knudtson. Welcome.
Thanks for having me.
So as we're looking at this SimpliVity platform, we need to drill deep into it, and this is one of the things I like, is that we can get really nerdy into the depths and the insides. What have we got in this bit?
Yeah, so this time we've talked a lot about the data virtualization platform, or DVP as we call it, because data virtualization platform is a long word. We've talked a lot about that. That's really the core of our technology and our software innovation. So we wanted to go a little bit deeper into that and talk about how the data virtualization platform enables deduplication, how deduplication enables a lot of the really cool features that we'll be talking about today.
And that was one of the things that really struck me as I was learning about the solution, as I was doing the first bits of work, is just that there's a lot of consequences of that always on, always happening deduplication, that you really need to start from the idea that you can have deduplication all the way through the product, and then there's a whole heap of benefits that flow from that. And so understanding that deduplication and those benefits is really important. Yeah,
and a lot of customers will automatically assume deduplication on all the time, performance is going to suffer.
Because all deduplication is the same as far as many people are concerned, and drilling into the details of how this works and how it's different, I found really interesting.
Yeah, and when you consider technologies like RAID that have been around for a very long time, people understand the variations between all the different implementations of it. Deduplication is relatively new in the industry, and particularly in production workloads. So we're starting to see some variations in how it's used, and traditionally it was to save disks.
So it's all about saving capacity.
Exactly. With SimpliVity, we look at it as a way to save I/O, which is really saving performance. It's saving performance for actual workloads as opposed to the additional things that we do under the covers, the backups and the replication of data and clones and that kind of stuff is stuff that takes away from actual production workloads, which is why we do backups off hours.
Right. Well, rather than talking about it, let's talk about it.
Yeah, absolutely. So what you see on the slide here is kind of some animation, some graphical ways of looking at it, because it would take me thousands of words to do it. So let's do it in pictures instead. So the first thing was to make everything simple. So if I'm creating a clone of a virtual machine, let's make it as simple as possible. So it's right-click on a virtual machine anywhere in the vSphere interface, and you've got access to the SimpliVity clone operation. What that creates is a fully independent virtual machine. So that virtual machine is able to be separated. I can delete the original virtual machine. There's no concept of a linked clone. There's no chain of snapshots. The concepts of differential and incremental backups just don't exist for us.
And this is all about the use of deduplication underneath that enables that independence.
Yeah,
and particularly the way the deduplication is structured on SimpliVity enables the independence so much more easily.
Yeah, and we're all of the data is shared between all the virtual machines because it's deduplicated. We never write the same block twice, but the way that we track the data and we manipulate the data lends it so that no one virtual machine can affect any of the other virtual machines. They more or less become immutable once they're written to disk. And then, of course, that leads to some really awesome benefits. Most deduplication tends to focus on the capacity, and when people look at the dashboard that you see there on the slide, they tend to think, oh, well, that's a lot of disk I didn't have to buy to get all that capacity. When we look at it and say, well, that's a lot of disk I didn't have to buy to satisfy I/O. So if I want to do backups every 10 minutes of a particular virtual machine, a high transaction virtual machine, the impact of taking a backup of that every 10 minutes in a traditional storage environment would be huge.
Even if it's just a VMware snapshots applied and then is committed again a few minutes later, that's still going to be a significant performance impact to the VM.
Exactly, yeah. I mean, at some point, traditionally, we're going to rip data off there, which is a lot of read I/O. With SimpliVity, and you'll see here in a second, we don't have to move all that data. It, again, is tracked in metadata and makes it very easy for us to make those backups. So what we've got here is a depiction of the data virtualization platform, where we've got, at the very top is the presentation layer. This is the interface the hypervisor uses to talk to our data management layer, which is the bottom two. The data management layer is then broken into the file system and object store. The way things lay out in there is, if you think about it as a tree of metadata, that very top ends up being like our VMDK. That's what we're presenting out. That's how vSphere, in this example, would be able to talk to its data, is through a VMDK. Below that, we link directly to a piece of metadata. And that one piece of metadata is essentially describing the entire virtual machine. So with that one piece of metadata, we know we're talking about that entire virtual machine and all of the data that it contains. At the very bottom, we've got the actual data. Those are the blocks that the virtual machine has written, and we track those and all of the relationships up the tree there. In this way, the file system really is just about tracking the relationships. That's its primary purpose. We get down to the object stores where all the data and the metadata is actually stored. Now, as we look at how, when we actually store data as it's being written, only the unique blocks actually get written into the object store. So as blocks come down, we investigate it. That's where the OmniStack accelerator card comes in that we've talked about. That will check it and see if it's seen it before. When it's something that we've seen before, that's not unique. There's no point in wasting I/O trying to write that to disk, even to a cache or some sort of pre-stage environment. Mm-hmm. It's sitting on the accelerator card. We find a duplicate, we throw it away, and now we've saved ourselves I/O. Now, as we go up, we actually look at the metadata, and you can see that the metadata and the actual data are stored equally. They're blocks of data. Even metadata takes some space. The idea is it takes less space, but it's all being stored down there, and only, again, the unique metadata gets written down. And we'll see here later on where that actually comes into play. So now we've got that virtual machine and all of its data written, and you can see from this simple example that we've already reduced the amount of load that has to go down to the disks. Now, when we want to do a clone of that, it's really easy with the SimpliVity environment because we're able to make a copy of essentially that top metadata. Mm-hmm. And since that describes everything, and everything at the moment the clone is created is 100% identical, it's easy to make that. And now we don't have to actually write any data. We don't have to read any data because it's 100% duplicate. And since we never write duplicate data, there's no reading or writing that has to occur.
And so it's just a single entry in that file system to say there's a new object that starts here.
Yeah.
That you can find under this top level metadata item, and everything else just fans out below it to exactly the same data.
Yeah, because the file system is all about interpreting the relationships between things. We say, hey, we've got another instance of M7 here, and it says, good, I know everyone else that comes in underneath of that. So that leads to some really great advantages: the simplicity, the speed at which we can do things, the independence of the data, and being able to drastically reduce not only capacity, but more importantly, the I/O.
Because that independence and the immutability you talked about was that each of those objects that's stored as unique never gets overwritten, never changes.
Exactly.
And so having two objects that both point to that M7, well, they're identical objects, but they both point to the M7 never changes. Yep. Yet the two objects that point can each change, and then they'll point to a different top level of that metadata tree.
Yeah, and what we'll get into here next is writing data. So if I write additional data to that, what happens? So again, we're being more efficient when this data is optimized in this way. And being able to use that upper level metadata to describe the things below it makes it easy for us to track changes and understand that when a change happens, it's a change for that virtual machine, not a change for the actual underlying block. So going back to our depiction of the DVP, we can see we've got a virtual machine. That's that same virtual machine 2 that we cloned earlier. All of its metadata and data below that. Now, what happens if I want to write love in front of hyperconvergence? Because, we all love hyperconvergence. So we've got this new set of data. That set of data has a relationship on top of it, so it's got a piece of metadata to describe it. So we see it ties into the M5. Well, M5 describes M1 and M2. So now that relationship that it's tracking has actually changed. So guess what we need to do? We need to change M5 because that does no longer describe its children.
Because the actual block M5 still says it's just points to M1 and 2, but we now need something that points to M1, 2, and 8.
Exactly. So now we get M9. So now that M9 we've changed to M9, we've got M7 up above there that describes
M8 and 6 it was before.
Yeah.
No, sorry, it was M5
5
and 6.
Yeah. It's hard to keep track of these when they start changing. That's part of the beauty. So M7 now is no longer describing its proper children, so now that's got to change. So now we actually change that to M10.
So changes ripple up through that tree from the bottom.
Exactly. So it's, again, we're not changing the data in the object store. What we're doing is we're changing the relationships above it.
but M7 and M5 still exist in their original form because we have VM1 that was cloned to make VM2, and if it hasn't written anything, it still needs those blocks.
Exactly.
And there again is the independence.
Yep, exactly. So now as we run through this and look for deduplication of the data itself, we're already seeing, hey, we're hitting a lot of data that we've already seen. We're going to ripple up through the metadata as well and find, yeah, those are 3 new pieces of metadata we've never seen. We've never seen the relationship of LOVE before. So there's a new piece of metadata to describe that. So the end of that ends up being, it's very, very unique architecture. This is not how anyone else is doing it this day. And being able to use that level of data tracking to be able to really make deduplication hum.
Yeah, so you're deduplicating the actual data that makes up the virtual machine, but you're also deduplicating all of the metadata as well. It's not
Correct.
like a lot of other deduplication schemes where you have a unique block store plus you have an ordered list of unique blocks that make up the data. Those things aren't separate. You don't have to copy the whole list of blocks every time you clone an object. It's just copy a pointer to the top object.
Yep, exactly. And that's a great softball for the next topic, which is being able to take remote backups.
Yeah, it's a little surprising because I haven't seen these slides.
Yeah, these are relatively new slides for us. So the remote backup capability is a huge part of the SimpliVity value prop. So we see most of our customers implementing multi-site implementations because it makes it so easy to move data. And in fact, this approach to tracking metadata is very efficient. And we've seen customers who thought they'd never be able to move their data over in a 24-hour period or implement DR because their pipes were just too small, actually have that option available to them now. And even with that first remote backup, we have a customer that backs up everything over a satellite uplink. So very high latency, very low bandwidth.
Low throughput.
And so, their biggest challenge was just getting things off the ship onto shore. And so they found the way SimpliVity did it actually made a huge difference. They were able to actually have 24-hour RPOs.
Rather than return to port.
Exactly. Return to port, plug the cable in to make it completely copper-based and hope it gets off in time before they have to ship back out again. So what we have here, again, is our DVP with the multiple layers, but we've now separated to 2 separate sites. So we've got our primary site, we've got our remote site. So think of this as a primary DR type scenario. And what we have here is 2 virtual machines. So we've got our Love Hyperconvergence virtual machine that we were looking at before, and we've added VM3 in here as well that has Love, Hype, or Hate It. What we're going to do with that VMO3 is show all the data for both sides, but we're going to push that VMO3 kind of back to the side. It's still there. All of its data is still in active use, but we're not going to reference it directly.
So this is two VMs running at 2 different data centers. They happen to have some data that's common across the 2 of them as is usual, and some that's unique.
Yeah. So in this scenario, you could think of, I've installed 2 Windows virtual machines, one out on the ship, one on shore, and they happen to have some commonalities because they happen to have the same operating system. So what we want to do now is we want to take that VMO2 and we want to back it up to that remote site. So that top level metadata is the first thing we're going to start with. Like you said, we can start at the top and we start understanding what's below it simply by sending it across. So we send across that M10 block and we look at it. Yep, it's unique. Let's get it down on the object store. So now we've persisted that block. Now the cool thing about the file system and its ability to interpret relationships is built into that metadata. We actually have an understanding of its children. So now, once we have that piece of data, that piece of metadata over there, we can investigate it and say, oh, it's got children. Those children happen to be M9 and M6. So looking at that now, we can start to investigate, hey, do we already have that? Are either of those unique? So we start with each child object. If it's unique, we're going to transfer it across. If it's not, we simply need to reference the existing block, or piece of metadata in this case, that is already resident in that remote site. So in this case, M9 is unique. We're going to move it across. We're going to store it down in that object store so that we have it persisted. And now we know what its children are. So we look at its children there, and we've got M8, M1, and M2. Looking at our object store, we're able to see, hey, wait a second. We've seen these 2 pieces of data. M8 and M1 are already in our object store. So guess what? None of that needs to be transferred, and none of its underlying children, its grandchildren in this case, need to be transferred either. And if there were great-grandchildren or keep on going down the road.
And that's the magic of that tree of uniqueness.
Yeah.
That as soon as you find at the head end that it's unique, or that you have that content already, you definitely have all of the children content from it.
Exactly. And that's because, no matter where in the world these SimpliVity nodes are, they're calculating that metadata the same way. And the fact that metadata is descriptive to its inheritance, its children, then everything's going to be the same no matter what site we're at. So it makes a common language that they can talk about. So
there's a whole heap of bandwidth and throughput saved by not having to pull that, not even having to pull the metadata, let alone the actual data underneath.
Exactly, yep. And it's not just saving the 10 gigs of Windows install, but it's also the metadata above that puts all of that 10 gig together. So now we essentially just keep going across and down, looking at each piece of metadata and saying, okay, well, if I don't have it, send it across, ship it down into the object store, and now I can investigate its children. So we simply just start moving down through this entire tree and looking through that level of metadata. As we go through the metadata, and we start recognizing other duplicates, and now we don't have to transfer that data. And this continues this way. So we look metadata heavy when you first look at it. It's like, okay, well, instead of having one block for one metadata for each block of data, we actually have multiple layers. So we're a little metadata heavy in that regard. But when you consider the movement of data and the ability to say, hey, we can find huge chunks of the data that's duplicate by simply investigating the metadata, this is where it really starts to hum.
But what we've seen is that the metadata itself is deduplicated. So when you look down a single object, you see a lot of metadata, but a lot of it's shared across multiple objects.
Exactly.
So the appearance can be a little deceiving when you look at a single object.
Yeah, and the objects are tracked at AK block level. So we've got the fairly high potential of duplication there because we're not hitting the really big chunks at a time, which lends to better deduplication potential. Of course, as we transfer data over that we find to be unique, in this case C, we'll automatically be able to tell, oh, well, we've got another C in there. I don't need to transfer that over.
I've already brought
this. Yeah, it wasn't here before you sent me this backup, but now that you've sent me some of your data, I can recognize it. And theoretically, that could happen in the metadata as well. So maybe love is in there twice in that particular virtual machine. I've now saved myself that love having to send it across twice. And of course, it continues on that way until we get to the last block. And then we can find that, hey, when we look at it, what we had before and what we had to send over, we can see what's circled here is the stuff that we had to actually transfer. So that whole virtual machine, love hyperconvergence, only required us to move 3 pieces of data and 6 pieces of metadata. That's a huge amount of savings when you consider all that data that we didn't have to transfer, that already existed.
Even when you look at the deduplicated size on the source, we've only brought probably a third of the VM across in this example, or at least a third of the word.
Yeah.
It's even though we deduped it at source, we're not pulling the whole dedupe data across. We're only pulling the unique.
Yep, and not even the whole description of it at that point either. So, again, that may be the Windows install plus maybe SQL's installed on both those virtual machines, or maybe it's some common file that a business puts on every one of their servers to track it for some reason. It could be the install of antivirus or other common systems like that. So in the end, we look at the OS plus applications plus data. Generally, what we see is mostly just the data has to be moved over. So to your point, in a very simplistic diagram like this, we're talking about only a third of that data being likely to be unique from each virtual machine. And that's a whole huge advantage of moving data between sites, which is a huge value prop for SimpliVity.
Excellent. So the data virtualization platform is absolutely core to the value proposition for SimpliVity, and it certainly took me a little while to think through and how it works and what all of those benefits are. So do keep checking out more of the videos that we're doing with the SimpliVity HC380 solution and think through more of the ways that it can help you as well.
Yeah, definitely, and it's an amazing technology, and this deck was one of our biggest animations to put together to be able to describe this. And I oftentimes call it the aha deck because I've seen you and a lot of other kind of industry analyst type people be able to see it in this format, and then that's when a lot of light bulbs have gone off. So it's been entertaining to see that for sure.
Yes, indeed. Well, it's been awesome. Thank you, Brian.
Yeah.